All right, so last time I was talking about how light it has an overall effect of seeming to slow down, but it never actually slows down. And what's happening is in these different substances, the photons are being absorbed, re-emitted, and that takes time. Like for example, in diamonds, it that takes them a lot of time. And as I was saying before, there is this substance that we can actually make in our laboratories where we can actually slow the speed effectively. That's a better way to put it. Effectively slow the speed of light down to walking speed, right? So you know, which is a pretty amazing thing. It's not it's this Bose-Einstein condensate is not a typical thing that you find in nature. We have to actually create that stuff in our laboratories. All right. So anyhow, that's a different story. But this thing where light is slowing down in these different materials, this value is reflect. This is what's called the index of refraction. Well, not this, but we're going to encounter a thing called the index of refraction, which you use in Snell's law as well. Strictly speaking, photons of light incident on glass are not the ones that travel through the exit, right? Because they get absorbed and then re-emitted, and re-emitted. All right, let's see. So this is the law of reflection, a very simple law. So one thing that's important, and hopefully you saw this in lab, or you if you haven't had the lab yet on Snell's law, you will. So with any surface, even if it's a curved surface, by the way, like we use in astronomy, if the surface, you have to have what's called normal to the surface. That is, there has to be a line. It's usually just an imaginary line that is perpendicular to the surface, and so that you measure the angle with respect to that line, right? So you draw a normal line, which is of course at 90. This is 90 degrees to the surface of this. This surface is nice and smooth. It's nice and flat. So if you have an incident ray come in, you measure that angle with respect to the normal, and like this one would be about 45 degrees. Let's say I'm just making that up. And if it was 45 degrees on this side, then the ray of light would reflect at the same angle. The angle of incidence equals the angle of reflection. So that's the way this works. And if you have a flat mirror, it's very simple. It's a very simple calculation. I don't think we're going to do anything with the convex or concave mirrors, but that makes things a little bit more complicated. All right. One other thing, of course, is that an object will always appear just as so. It'll appear the same distance behind the mirror. Of course, it's not physically behind the mirror as the object is in front of the mirror, right? So you have these rays of light, and they seem to converge at a point behind the mirror, which would be exactly the same distance that the object is in front of the mirror. And by the way, we call this so the image, when you have a mirror like this is actually called a virtual image. So because the image is not physically there, it just seems like it's there. All right. So the way that we distinguish between a virtual image and a real image, like for example, when light passes through a lens, there's a real image there because the light is actually passing through the lens. Anyhow, if you put a screen right here, behind the mirror, you're not going to get the image of the candle. That's because it's not, that the image is not coming, it's not really getting there. It's the light bouncing off the mirror, and it's appearing to come from that distance. All right, so that's plane mirrors. Let's see, curved mirrors can, of course, we do have curved mirrors. So we're not going to get too much into this, but like if you have these curved mirrors, things can look smaller. If you look usually out the left hand side, the the passenger side of a car, it'll say something like, objects images in this mirror are closer than they appear, and that is because you're using this kind of a mirror right here. This is what's called a concave mirror. I'm sorry. Let's see. This is a convex mirror. Sorry, it's a convex mirror, and that usually happens on the passenger side of cars, and what that does, it allows you to see a little bit around the corner. That's a desirable thing. And then, of course, this kind of mirror, where this one is a concave mirror, the one on the right hand side. This one on the left hand side is the convex. This one's the concave, and that one, for example, people use this like a makeup mirror, for example, will kind of enhance. It makes your image look a lot bigger. If you want to see fine details, that's like when people are putting on makeup or something like that. I don't know. Anyhow. All right. The next one is what's called diffuse reflection. So if the surface of something is really rough, and what do we mean by rough? It's got to be, the mirrors, both the flat, the plane mirrors, and the concave and convex mirrors. Convex and concave mirrors are not rough at all. And what we mean by rough is, compared to the wavelength of the light, the mirror is relatively smooth. So there's a certain distance between waves, and so if that is bumpy compared to the wavelength, then you get what's called diffuse reflection. Right. And so sometimes that's actually desirable to have diffuse reflection, but sometimes it's not desirable. Anyhow, this is just a radio telescope. So this is, even though this looks like a mesh, and, of course, light rays would go right through most of this, radio waves, which are physically bigger, will go into this thing, bounce off of it, and reach the detector right up here. All right. Let's see. So this is what they're going to talk about here is what's like mirages and things like that. So sometimes you encounter mirages. All right. So this is we have to first understand what's called refraction. And so when light goes from this is exactly the lab about Snell's law. When light goes from one medium, like air, to using an example of a car going from the road to grass. What happens is the speed changes, and so the angle will change, right? If you come in at a certain incident angle, what's called the refracted angle will be different. And this is the basic idea, right? So you come in at some angle with respect to the normal, and then as it goes through the water here, or whatever the substance is, whatever the medium is, it bends. All right, and you see this all the time. Like if you take a pencil and you put it in some water and you have a beaker, it looks as though the pencil is bent, but it's not bent at all. It just looks bent because of refraction. Let's see. Refracted rays bend towards the normal as the light has slowed down. Right. More questions. So refracted rays that bend away from the normal is that the light has sped up. So this is actually something that if you go spear fishing for some bizarre reason, it's not bizarre. I shouldn't say that. If for some reason you find yourself spear fishing, you have to aim. So for example, the fish will appear slightly higher, because our eyes, all we're doing is we're just seeing the photons of light coming, and we're not imagining that, our minds are like, oh, this is just coming from us at a straight line, but really, because the fish was in water, the rays are bent away from the normal, as they leave from the water to the air. And so when you project back a straight line, the fish would actually be a little bit closer to the surface. And so people who spearfish know this, and you have to aim a little bit below. Um, and it depends on the angle that you're looking at and stuff like that. All right, so anyhow, this is also something that takes place with the sun. Believe it or not, when the sun sets, it's actually a little bit below the horizon, because the light is being bent by the Earth's atmosphere. This is the thing that I was mentioning before, the mirage, and so this is over the course of a really hot day. Let's say the light is being bent, especially around roads, right? Because of course the air right above the road is extremely hot, and so it can bend the light, and you can see an image, like way down. It looks like it's down here, for example, which would not exist if light didn't show, didn't slow and transparent mediums. You wouldn't have any of them yeah, that's right. All right. Let's see. So color. Now, color. So of course, we learned this at the very beginning, that color is just different frequencies. Now, when we color things, of course, it's really a mixture of different colors, right? Like, for example, as it says here, there's 7 hues, red through violet, and when you group them together, you get you get like all of them at the same time. You get kind of a white appearance. All right, so now in glass, of course, what happens is the red light will bend the most, and the blue light will bend the least. As a matter of fact, and that is just a property of having different. So in other words, the different wavelengths actually have different indices of refraction. So that's what happens. All right. All right. So this is how color is created. Using either projectors or even in your television. Right. It just there. I mean, it's more complicated than this inside of. It's actually. Certain molecules that when they get excited, will emit red, red, green, blue, and different combinations of them will give you all the different colors. Right. So, this is some dispersion. So this is what I meant. In fact, Isaac Newton was the one that proved that white light was composed of all the colors of the rainbow. So you take a prism, and the light the red light will bend, and you know what? I made a mistake earlier. I said the red light bends the least. Sorry about that. The blue light bends the most, right? Because the blue light has a shorter wavelength. Sorry about that. All right. So white light passes through prism. The green light is bent more than the blue light. Oh. More than the red light. Oh yeah. Sorry. So I always get those backwards. So the blue light bends the most. Then comes the red light. All right. So green light would. So let me read how is it? The green light is bent more than the red light. Yeah. Okay, that makes sense. Rainbows are actually. So when you see a rainbow, you're actually seeing the light dispersed in a single drop. Here's an interesting fact: is that when you look at a rainbow, everybody sees their own rainbow actually,